Hey everyone, and welcome to this explainer. Let's just jump right in, shall we? Today, we're tackling a massive, jargon-heavy world that literally powers almost everything we do, the global oil and gas industry. If you've ever looked at a towering refinery or one of those sprawling offshore rigs and thought, how on earth do engineers make sense of all that chaotic complexity? Well, you are in the exact right place. Think of this massive industry as a fascinating, incredibly intricate puzzle. And today, we're going to decode that puzzle together, step by unlocking the process engineer's essential toolkit. Okay, let's dive into this crash course syllabus. We're looking at four foundational pillars today. First up, the three streams of oil. Then, the engineer's master map. After that, the API engineering rulebook. And we'll wrap up with the process safety net. All right, starting right off with section 1, the three streams of oil, navigating the industry's massive macro environment. To really wrap your head around this industry, think of the entire petroleum value chain as, actually, scratch that. Think of it as a giant living organism. This organism breathes, moves, and transforms raw materials, managing hydrocarbons in totally different physical states, under extreme pressures, and across vast distances. Engineers divide this beast into three distinct sectors. First, you've got upstream, or E&P. This is all about extraction, finding and bringing raw hydrocarbons to the surface from deep underground or subsea reservoirs. Next up is midstream. Think of this as the logistics nervous system. It's that continent-spanning network of pipelines, compressors, and tanks, moving those raw resources from the wellhead straight to the refinery. And finally, downstream. This is basically a continuous, city-sized chemistry experiment, where crude oil and gas are processed using extreme heat and complex catalysts into the stuff we actually use every day, like gasoline, jet fuel, and plastics. Because each sector deals with completely different states of matter and pressure, the equipment they use is just uniquely massive. It's awe-inspiring, really. Upstream equipment, like blowout preventers and drill bits, well, they have to contain violent, totally unpredictable subsurface pressures that can easily exceed 20,000 psi. That's insane. Midstream relies on heavy-duty centrifugal compressors and pig launchers to efficiently shove fluids across thousands of miles of steel pipe without losing pressure. And downstream, that sector uses towering distillation columns and heat exchangers to safely handle extremely high temperatures. We're talking over 500 degrees Celsius, along with highly reactive chemical catalysis. The scale of this and the specific engineering challenges they face are absolutely breathtaking. Moving right along to Section 2, the engineer's master map, translating complex industrial blueprints. So, to navigate this massive machinery safely, an engineer needs an incredibly precise map. Let's be real, you can't just stroll into a refinery and guess what a pipe does. You need a document that speaks the industry's universal language. Here's how it builds from concept to reality. First, engineers start with a process flow diagram, or PFD. This gives you the broad conceptual strokes, the fundamental process design, major equipment, and primary operating conditions like flow rates, temperature, and pressure. But when it's time to actually build, operate, or troubleshoot the plant, that's when you need the piping and instrumentation diagram, the P&ID. This is your detailed, meticulous mechanical blueprint. It shows absolutely every single interconnection, all the equipment, exact piping specs, every valve, and all the complex control instruments that keep the system running. Now, what's really interesting about this slide is that you aren't just looking at random lines on a page. You're seeing physical sequences and connections. You can literally trace the exact flow path of the fluid. You can spot the location of crucial safety relief valves, check the precise piping line specifications, and locate specific equipment numbers. It shows the operator exactly how systems can be isolated for maintenance and, crucially, where the hazard points are. Of course, looking at a P&ID for the very first time can kind of feel like staring at alien hieroglyphs, and that is exactly where the legend sheet comes in. This document is essentially the translation key for a secret language. It defines standard symbols for every pipe type, sensor, piece of equipment, and valve used in those drawings. And it's all heavily based on strict ISA and ANSI standards. Before an engineer or operator can even begin to read the map, they absolutely have to master this legend. Which brings us to Section 3, the API Engineering Rulebook, the non-negotiable laws of survival. Having a map of the facility is absolutely critical, right? But just having a map isn't enough. You have to follow the strict laws governing this highly volatile environment. As our sources point out, and this is a great quote, equipment doesn't fail suddenly. It fails when standards are ignored. Talk about a powerful reality check. The standards set by the American Petroleum Institute, or API, well, they aren't optional reference materials or suggestions you might look at later. No way. They're the absolute, non-negotiable engineering rulebook of the oil and gas industry. They govern exactly how equipment is designed, manufactured, tested, and maintained to prevent catastrophic failures. Let's break down a few of these heavy-hitter API standards. Take API 610, for example. This covers centrifugal pumps. In a processing plant, rotating equipment like pumps act as the literal heartbeat of production, constantly pumping the lifeblood of the facility. Then you've got API 6D, which dictates strict requirements for massive pipeline valves, making sure they have a full bore design so maintenance tools, which are called PIGs, can travel straight through them. And we definitely can't forget API 682 for mechanical seals. Those are your primary defense against leaks, fires, and frequent shutdowns on rotating shafts. So why does all this matter? Because ignoring these standards carries literal life or death consequences. A perfect example of this is the NASE MR0175 standard. You see, many global reservoirs produce what's called sour gas, which contains hydrogen sulfide, or H2S. It is highly toxic and incredibly corrosive. If you just go and use standard high-strength steel in an H2S environment, a phenomenon called sulfide stress cracking happens. The gas will literally make the steel so brittle that under immense pressure it will shatter like glass. It's terrifying. This specific standard dictates the exact metallurgical chemistry and hardness limits required to keep that equipment from violently exploding. And that segues perfectly into Section 4, the Process Safety Net, designing fail-safes for extreme hazards. We've seen the map, we've learned the laws, but what happens when the unpredictable inevitably happens? Because hydrocarbons are inherently flammable and toxic, engineers must design critical safety studies and fail-safes to keep the entire facility from going up in flames. This safety net begins before the plant is even built, with a HAZOP, or Hazard and Operability Study. This is a rigorous, highly organized brainstorming session. A multidisciplinary team of engineers takes that P&ID blueprint we looked at earlier and breaks the complex design down into simpler, bite-sized sections called nodes. Using their collective imagination and standard guide words, they systematically brainstorm every single possible thing that could go wrong. What if the pressure spikes? What if a valve fails closed? It's a vital qualitative review designed specifically to catch engineering blind spots. But here's the thing. Safety can't just be a qualitative what-if session. It requires hard math. That's where the safety integrity level, or SIL assessment, comes in. SIL takes safety from a brainstorming session to a rigorous, calculated measurement of risk reduction. It defines 4 levels of dependability, with SIL 4 being the absolute highest. The whole goal of a SIL assessment is to mathematically demonstrate that the risk to personnel and equipment has been reduced to ALRP, which stands for as low as reasonably practicable. It defines exactly, down to the numbers, how dependable the automated safety systems have to be. And this brilliantly illustrates how all of this safety theory translates into physical protection. The Emergency Shutdown, or ESD system. Think of the ESD as the plant's automated biological reflex action. If field sensors detect a fire, or maybe a sudden drop in pressure signifying a ruptured pipeline, or a toxic H2S leak, they instantly send a signal to a logic solver. Faster than a human could ever react, the system automatically triggers these massive, heavy-duty master valves to slam shut, instantly isolating the hazard and saving lives. From extracting hydrocarbons from deep beneath the earth in the upstream sector, to transporting them across entire continents in the midstream, to breaking them down chemically in the downstream refinery, we've covered a lot of ground today. We've decoded the massive master maps, the rigorous API standards, and the crucial safety nuts like HAZOP and SIL that make it all possible. It is a world of millions of interlocking valves, miles of steel pipe, and immense, violent pressures. It is, without a doubt, the ultimate industrial puzzle. So the question is, with this Process Engineer's Toolkit in hand, are you ready to learn more and master it? Thank you so much for joining me on this explainer, and keep exploring.